Okay, so this is my second time recording this video, which is a little frustrating, but anyway, that was my own fault. Okay, so what we want to have a look at today is the basic graph shape, y equals sine of x, y equals cosine of x, and then start to look at applying some of our transformations to that shape to sketch graphs. Okay, so let's get straight into it. So what we're looking at here is the y coordinate. So we need to be distinct between the x and y coordinates of the points on the unit circle and the x and y coordinates of the points over here, which are representing different things. So in this case, what our x-axis is representing is the angle in the unit circle, and what our y-axis is representing, in this case, is sine of that angle. Okay, so what we want to look at is, as we change the value of the angle, how does the value of sine change? Okay, that's what we want to plot. Alright, so let's just work our way around in the unit circle and have a look at some key points. So when the angle is 0, the sine value, which is the y coordinate at this point, is also 0. So the graph's going to go through the point 0, 0. When the angle is, let's pick one angle in between here just to give us a bit of a guideline. When the angle is pi on 4, the sine value is that. So there. Oops, sorry. When the angle is pi on 2, the sine value is the y coordinate at that point in the unit circle, which is 1. When the angle is 3 pi on 4, I have the same sine value, as when the angle was pi on 4. Okay, so we're going to have the same value there. Those 2 points will have the same y coordinate because they have the same sine value. When the angle is pi, the sine value will be 0. When the angle is 5 pi on 4, the sine value will be that. So about there. When the angle is 3 pi on 2, the sine value will be -1. When the angle is 7 pi on 4, the sine value will be the same as what it was when the angle was 5 pi on 4. So it will be here also. And when the angle is 2 pi, it will be the same as when it was 0, and we'll be back to here. And if we were to continue around the circle a second time, we would see the same things happen again. Okay, so at 9 pi on 4, it would be the same as pi on 4. Okay, so we get the exact same thing happening out here, and we could continue. Similarly, if we continue around in the negative area, we're going to see the same thing happen again. So traveling from negative pi in the unit circle around to 0 is exactly the same thing that happens when we go from pi around to 2 pi. So exactly the same points that we saw in this section should be exactly the same here. Okay, and we can confirm that. So for example, at negative pi on 4, the value of sine is going to be here. At negative pi on 2, the value of sine is -1. At negative 3 pi on 4, the value of sine is the same as it was at negative pi on 4. At negative pi, the value of sine is 0. Okay, and we can join up those points to plot out the basic shape of y equals sine of x. Now obviously the domain of this function is R. It can go on and on forever. We can continue, same thing will repeat. The range here is going from -1 up to +1. Okay. Alright, let's think about cosine. So again, this time our horizontal axis still represents the angle, but this time our vertical axis represents cos of that angle. Okay, so the x coordinate of the point in the unit circle. So again, let's plot out some key points. When the angle is 0, the value of cosine is 1. When the angle is pi on 4, the value of cosine is that distance there. Now, interestingly, when the angle's pi on 4, the value of cosine is the same as the value of sine. But that's just because what we have here in the unit circle is an isosceles triangle, okay, because of the 45 degrees. So it will also go through that point. When the angle is pi on 2, the value of cosine is 0. When the angle is 3 pi on 2, the value of cosine is negative. Okay, so it's going to be negative this distance. So, if we sort of imagine that distance, it should be the same as this distance at pi on 4, but just the negative of that. Okay, when the angle is pi, the value of cosine is negative 1. When the angle is 5 pi on 4, the value of cosine should be the same as what it was for 3 pi on 4. Okay, they're the same cos value. When the angle is 3 pi on 2, the value of cosine, the x-coordinate in the unit circle, is 0. When the angle is 7 pi on 4, the value of cosine should be the same as it was for pi on 4. So it'll be the same value. And when the angle is 2 pi, the value of cosine is 1. And again, we can continue the same pattern around for the negative angles. The same thing that happens between what happens between negative pi and 0 would be the same as what happens between pi and 2 pi. Okay. And that's because they are literally exactly the same positions in the unit circle. So going to give the same cosine values and or the same sine values. Okay, so there we've got our cosine graph. I have got a previous video recorded a number of years ago which shows this in a lot more dynamic way, and I will link to that video on YouTube, so you can click to that and have a look at, in a really dynamic way, how those graphs appear out of the unit circle. But we essentially want to focus on this basic shape. Let's just think about domain and range here. So obviously the domain of the cos function is going to be r, and the range of the cos function is also from -1 to 1. Okay, let's look at some more features of sine x and cos x. So both of these functions are what we call periodic functions, and that is that they repeat, and they repeat over a fixed period, range that we call period. Okay, so what we're looking at here is, and we can see that from the unit circle, we know that once we've done one lap of the circle, we've seen everything. If we were to then look at the graph between, so from 0 to 2 pi, we're going to see exactly the same thing as we would from 2 pi around to 4 pi, which is exactly the same as what we would see from 100 pi around to 102 pi. Okay, so the whole thing is just going to continue to repeat on a period that is just 2 pi. So once we've looked at a window of 2 pi for this graph, we can then just take that and rubber stamp it. So for example, if we look at a window that is 2 pi wide, okay, we can just take that graph shape and repeat it. Same again, same again, same again, etc. Okay. I want to be clear about the fact that it doesn't just have to be 2 pi starting at 0. So say for example, if we were to look at a window that's 2 pi wide from here to here, we see one complete period that we then just need to repeat and repeat. Okay. Similarly, if we look at one complete period, I'll change from the highlighter because it's a bit thick. If we look at one complete period, say for example from this point, if I travel on 2 pi from here, that's a distance of 2 pi. I take that much of the graph and I just repeat that and repeat that and repeat that, and I've got a full period of my graph. Sorry, just getting rid of that off my original graph. Same thing is true with sine. You look at one window of 2 pi, pick any point, 2 pi further on from there should be the same y value, and you take that picture of the graph and you repeat it, repeat it, repeat it. Okay, so the period of both the sine and the cos graph is 2 pi. Y equals sine x has a period of 2 pi, y equals cos x has a period of 2 pi. Period being the length of one cycle. The window in which you need to look to see one complete period, you can then take that and rubber stamp it to draw the whole function. Both these graphs also have something called amplitude because they are oscillating functions. Okay, they go, in this case, up and down and up and down and up and down and up and down. They oscillate about the x-axis. Okay, both these graphs oscillate about the x-axis. The amplitude of an oscillating function is the maximum distance that you travel away from that central axis. So we go up by 1 and then down by 1. We go up by 1 and then down by 1 relative to the x-axis. So our amplitude is 1. Same for both the cos and the sine curves. So amplitude of 1, amplitude of 1. Okay, now what we want to look at is to start to apply our transformations. So we're going to look at graphs of the form y equals a times sine of nx and y equals a times cos of nx. Okay, so we should be familiar with these. If we just think about the a, we're looking at y equals f of x becomes y equals a times f of x. We should be familiar with that as a dilation from the x-axis by a factor of a. Focusing just on n, we're looking at, y equals f of x becomes y equals f of nx. A dilation from the y-axis by a factor of 1 over n. Let's just have a quick play around with that. I'm just going to change across to a graphing program. Okay, so here we should be able to see this is the graph of y equals a times sine of nx, where both a and n are 1. So this is just the graph of y equals sine of x. Let's focus on a first. So we talked about a being dilation from the x-axis, so we should expect, as we make a bigger, the graph dilates away from the x-axis, and it is therefore the amplitude of the graph that's changing. If a becomes something less than 1, that's fine, it's still a dilation from the x-axis, it's just squashing the graph, so the amplitude is getting smaller. If a were to become negative, we should be able to think about what we expect from other graphs. Obviously if a is 0, it's just y equals 0, it's not a sine graph at all. But if a is a negative value, we're actually seeing that our sine graph reflected in the x-axis. So instead of it going, if we're starting at 0, instead of it going up first and then down, we're now seeing down first and then up. So at the moment a is negative 1, this is the graph of negative sine of x, and it's simply just the reflection in the x-axis. If we make a more negative than that, we've got two things happening, reflection in the x-axis and dilation by a factor of, in this case, 1.3. Okay, if I make a back to 1, and we focus on changing n, so remember when it's inside the function it's sort of backwards. So f of nx is a dilation of f of x by 1 on n from the x-axis. So what we're going to see here is as we make n bigger, we're dilating by, in this case let me just go to a whole number so we can be clear about what's happening. N is 2, we've dilated by half from the y-axis. So where the period before was 2 pi, we're now seeing the period is pi. We're seeing one complete revolution of the sine curve, one complete picture of the sine curve between 0 and pi. So we've halved the period. If we make n, continue to make n bigger, we continue to squash the graph towards the y-axis because the dilation factor is 1 over 4 in this instance, and so the period becomes smaller. If we were to make n, so let's put n back to 1. Okay, if we were to make n smaller, if we divide by a number that's smaller than 1, we make it bigger. So if we, for example, look at when n is 0.5, the period has gone from being 2 pi to being 2 pi divided by 0.5, that is 4 pi. So we've stretched the graph out by a factor of 2 away from the y-axis. Okay, if n were to be negative, okay, we would again see, this time, reflection in the y-axis. So if n is negative 1, we've reflected the graph in the y-axis, but we don't need to worry about that with the sine graph, because reflecting the sine graph in the y-axis is the same as if we had reflected it in the x-axis. So we won't ever see negative n values, we'll just make a negative if we want to reflect it in the x-axis. In the case of the cosine function, making n negative would reflect the graph in the y-axis, but the cosine graph's already symmetric about the y-axis, so it doesn't actually change anything. So we wouldn't bother to worry about n being negative, but just it does follow from all of our other functions in that it is about reflection in the y-axis. Okay, let's go back over to the notes. And let's sort of summarize what we've observed there. So if we have the graphs of the form y equals a times sine of x and a times cos of x, the effect of a is to dilate the graph by a factor of a from the x-axis. So this will affect the period. Sorry, affect the amplitude if we're stretching from the x-axis. What happens if a is negative? So if a is negative, the graph is reflected in the x-axis, reflects the graph in the x-axis. So for the sine graph, that will mean the graph goes down and then up first. For the cosine graph, the graph will start at the bottom and then go up and back down. Okay. If we have graphs of the form y equals sine of nx and y equals cos of nx, the effect of n is to dilate the graph by a factor of 1 over n from the y-axis, and this will affect the period. If n is negative, it reflects the graph in the y-axis, okay. If you think about that though, a sine graph that's the original sine graph. If you reflect that in the y-axis, you get that, which is exactly what you get if you reflect it in the x-axis, so we don't worry about it. And if you have a cosine graph and you reflect it in the y-axis, it's the same thing, so we also don't worry about that. Okay, so we don't really need to worry about reflections in the y-axis. We won't really see these. We'll just really focus on a might be negative, in which case we get reflections in the x-axis. Okay, so let's bring that together then. If our function is a times sine of nx or a times cos of nx, the amplitude is going to be affected by that dilation by a factor of a from the x-axis, and so the amplitude is going to become a. Now I want to be careful about that, because if a is negative 2, the amplitude is not negative 2. The graph's been reflected and the amplitude is still 2. So technically what we want is the absolute value of a, which just means we ignore the negatives. Okay, I'm not too worried if you don't draw in those vertical lines. We don't cover the absolute value in maths methods anymore, but by that, yeah, I just mean the size of a. Okay, so if a is negative 7, the amplitude would be 7, the graph would be reflected in the x-axis. Period. So dilation by 1 on n from the x-axis means the period that was 2 pi is now being multiplied by 1 on n, and so the period becomes 2 pi on n. And that's the same for the cos curve as well. Okay. Again, if n is negative, that's not going to affect the period. The period is always a positive value, so technically absolute value of n. I'm not worried if you don't want to draw those vertical lines in. It's notation beyond the scope of this course, but I want to be clear about the fact there's no such thing as negative amplitude or period. If a or n are negative, that doesn't apply to how you think about amplitude or period. That's how you think about reflections. If a or n are negative, then the graph has been reflected. Okay, we've already talked about those in greater detail in the table above. You can have a look at which one's which. Okay, let's draw some graphs. What I want to be really clear about when we sketch a sine curve or a cos curve is what you want to focus on is getting one period right, and from there you're going to just repeat the pattern. Okay, so let's focus on one period of the sine curve. There's 5 key points that define it: the starting point, the ending point, so at the end of the period, halfway along the period where you'll be again at the average value or the central value, halfway between those two x-intercepts you'll have a maximum value, halfway between those two x-intercepts, the next two x-intercept you'll have a minimum. So those 5 red points are what you want to plot out and plot out correctly in order to get your sine curve correct. In order to do that, you're going to need a scale that certainly encompasses the end of the period. You're also going to need half the period. Okay, and you're also going to need a quarter of the period and 3/4 of the period. So what we want to do with our scale is to divide, to make sure the period is marked on the scale, but also then to divide the period into 4 equal units so that we can get our sine graph plotted out carefully. If you've got really erratic scale, 1, 2, 3, 4, and you're trying to plot a sine curve, you're going to have real problems getting your shape right, okay? So it's really important that you plan and you scale before you draw it. The same thing is true of a cos curve, okay? 1 complete period of cosine, okay? Again, starts at the maximum value, finishes at that value at the end of the period. Halfway along the period, it's at the minimum value. Halfway between the max and min values is where you get your x-intercepts. 5 key points define the curve. You're going to need the period, half the period, a quarter of the period, 3/4 of the period. So again, you want to take your period and you then want to divide that scale into 4 equal sections to help you plot out the 5 key points that define one period of a sine or a cos curve. It's really important, and that only becomes more important as we add in more transformations such as the translations, where things are really going to start to get quite complicated. Okay, let's think about these graphs. So first one is the sine curve with no reflection. So the shape, it's going to start at the center, go up, down, and back to the center. Okay, and then we might have more than one of those. But let's just focus on the basic shape for one period. The 2 out the front is going to affect the amplitude. The amplitude is 2. So my graph is going to oscillate between -2 and +2. And the period in this instance is 2 pi on n, so 2 pi on 3. We're going to see 3 complete periods between 0 and 2 pi. 2 pi on 3 times 3 is 2 pi, so we're going to see 3 complete periods. Okay, it's then about plotting out our axes. So when we're not translating up or down, which we're not doing at all yet, everything's going to center around the x-axis, so we want that to be in the middle, and we're sketching over this domain. Okay, so 0 to 2 pi, so thinking about axes that are suitable for that. So we want to go to 2 pi. I'm going to then just halve that pi just for sort of a key marker. Now, I want to think about the fact that my period is 2 pi on 3. So I'm going to need to be able to scale my axis in thirds. So I'm going to take this distance that's pi and I'm going to divide that into 3 equal sections. A bit uneven, let me try that again. You don't need a ruler, it doesn't need to be perfectly precise, but if you cannot do this vaguely accurately by eye, then use a ruler. Okay, so I've now divided it into pi on 3. Each of those is, so each of those ticks represents pi on 3. I'm not going to label them all yet, you'll have labels everywhere if you label everything from the beginning. So my period is 2 pi on 3. So I'm going to see one complete period from 0 to 2/3 of pi, which is that. Okay. As I've talked about up here at the top, we want to divide that period into 4 equal sections. Okay, just let me get rid of that arrow. So my period is going to be to 2 pi on 3. I'm going to need to divide that into 4. So it's already divided in half. I'm going to divide in half again. Okay, that's going to enable me to get my first period correct. Okay, let's plot some points. My sine list for the first period. My sine graph starts at 0, ends at the end of the period at 0, and has another x-intercept halfway along. So those 3 points my graph's going to go through. Halfway between those first 2 x-intercepts is where we'll have a maximum value. Now again, I'm going to rule in just a very faint pencil line. These aren't asymptotes. They're not features of the graph. You're not going to draw them in. They're just guidelines to help me get my graph straight. Okay? Because again, if you're not consistent about your maximums and minimums, you'll have graphs that, you know, go up and down and aren't even. Won't be that bad, but you'll see things like it'll gradually get kind of slightly smaller just because you weren't careful enough. So rough pencil line just to give you a guideline if that's a helpful thing to do. So my maximum value, so in this case, those pencil lines with that amplitude of 2 are at +2 and -2. Okay, and halfway between the second 2 x-intercepts is where we'll have a minimum value. So there is one complete and correct period. And then we need to repeat that until we've filled out our domain from 0 to 2 pi. So we needed our axes to be divided into half again. So I'm going to halve each of these, so I've got all the points that I need. And now what we have there is each of those units along the x-axis is worth pi on 6. 1 pi on 6, 2 pi on 6, 3 pi on 6, 4 pi on 6, 5 pi on 6, 6 pi on 6, etc. Okay, so now we just repeat. So every pi on 6, every time I go across pi on 6, I get to the next key point on the function. So we're currently in the middle of the average value, the x-intercept. Pi on 6 along from there will be at a maximum value. Pi on 6 along from there, we're back at the middle. Pi on 6 along from there, we're at the minimum value. Pi on 6 along from there, back in the middle. Pi on 6 along from there, maximum, back to the middle, minimum, back to the middle. Plot out your points, and then it's just an exercise in dot to dot. Smooth, symmetric, etc. Okay. Then we're going to label our key points. I'm just going to reduce my pen size. Things will get a bit crowded here. And again, it's just about counting. Remember, 1 pi on 6, 2 pi on 6, 3 pi on 6, 4 pi on 6, and simplifying your fractions as you go. Okay, so my first turning point is at pi on 6, 2. My first x-intercept is at 2 pi on 6, which is pi on 3. Unless it specifies in the question to label with coordinates, I'm not going to for the sine graphs and the cos graphs because they get very crowded very quickly. If you've got space to use coordinates, absolutely do. If the question specifies coordinates, you must make sure you label x-intercepts with coordinates. Right, 1 pi on 6, 2 pi on 6, 3 pi on 6, which is pi on 2, negative 2. 4 pi on 6, which is 2 pi on 3. 5 pi on 6. 6 pi on 6, which is pi. It's already labelled, but I'll label it again. 7 pi on 6. 8 pi on 6, which is 4 pi on 3. 9 pi on 6, which is 3 pi on 2. 10 pi on 6, which is 5 pi on 3. 11 pi on 6. And 12 pi on 6, which is 2 pi. Okay, and there's my complete sine curve. Alright, let's do another one. Sketch the graph of y equals 4 cos 4x. Okay, shape. Okay, hasn't been reflected, it's a cos curve, it's going to start at the top and finish at the top. So we're looking at that shape. Amplitude is 4. Period is 2 pi divided by 4, which is pi on 2. So between 0 and 2 pi, we're going to see, sorry, not two of them, we're going to see 4 complete periods. Okay, so again, let's think about our scale and our axes, the planning, invest the time in the planning, and it will be worth it in the long run, okay? 0 to 2 pi, I'm going to halve that, that's pi. I'm going to halve again to get pi on 2. That's my period. That's the end of the period there. And then this will be 3 pi on 2. So remember, we want to divide our period into 4 equal sections. So I'm going to halve it and halve it again. And that's going to enable me to get my shape right. I'm going to draw in some guidelines for my amplitude. Okay. So whatever distance you choose, it doesn't really matter as long as you've got guidelines same distance either side of your axes. Sorry, my axis bends a little, so it gets a bit crooked. And obviously with an amplitude of 4, in this instance that's 4 and negative 4. So amplitude doesn't really change how you draw the graph, it's just how you label the points really. Okay, first period, cosine graph starts at its maximum value. At the end of the period it'll be back at the maximum value. Halfway along the period, which is here, we're going to be at the minimum value. Halfway between the maximum and minimum, we're going to be on the x-axis, and so we've got those two x-intercepts. And then we can plot out the shape of our first graph. What you need to understand when you're drawing the graph, one error you'll make is that at the y-intercept here, that's a turning point. So you must make sure you get this sense that your graph is turning out of there. Often see students sort of draw a graph that pretty much goes straight down. So shape should be a turning point through your x-intercept. Oops, sorry, It's got a bit crooked there. Let's try again. Turning point through my x-intercept, ready to turn again at my minimum, through my x-intercept, turning again at my maximum, and then we're going to continue. So I'm going to divide my axis up. Each of these periods I'm going to divide it into 4 so I can get the shape right. The scale's a little uneven here, but that's okay, it's not too bad. Again, use a ruler if it's really bad. So we'll be back to the middle, down to the minimum, back to the middle, up to the maximum, back to the middle, down to the minimum, back to the middle, up to the maximum, back to the middle, down to the minimum, back to the middle, and up to the maximum. Join the dots. Okay, again, making sure you've got that turning point at the end. Okay, let's label our points. Now again, let's think about how big each of these, now I probably did get my guidelines getting a bit wider as we went, but again, doesn't need to be perfect, just make sure that things are vaguely accurate. So I probably should have kept this a little bit, sorry, not that bad, but a little bit higher up here. Anyway, okay, each of these ticks on my x-axis, so we've halved and halved and halved and halved again, basically. So this is going to be pi on 4 here, half of that then will be pi on 8. So each of those ticks is pi on 8. 1 pi on 8, 2 pi on 8, 3 pi on 8, 4 pi on 8, 5 pi on 8, etc. Okay, so we can just count our way along the graph. So y-intercept is at 0, 4. This x-intercept is pi on 8. This is 2 pi on 8, which is pi on 4, negative 4. What are we up to? 2 pi on 8, 3 pi on 8 for this x-intercept. 4 pi on 8, or pi on 2. 5 pi on 8. 6 pi on 8, which is 3 pi on 4. 7 pi on 8. 9 pi on 8. Sorry, 7 pi on 8, 8 pi on 8, which is pi. 9 pi on 8. 10 pi on 8, which is 5 pi on 4. 11 pi on 8. 12 pi on 8, which is 3 pi on 2. 13 pi on 8. 14 pi on 8, which is 7 pi on 4. And 15 pi on 8. And 16 pi on 8, which is 2 pi 4. Okay, having to draw 4 complete periods is quite a lot, so we've got a lot of points there. You know, realistically, you probably won't need to draw as many periods in an example. But if you do, again, any graph, x-intercepts, y-intercepts, turning points. If it doesn't specify coordinates for the x-intercepts, I wouldn't use them. It gets crowded very quickly. I would, however, use coordinates at the points for your turning points. If it's easy enough to rub out your guidelines, rub out your guidelines. They certainly shouldn't be drawn as if they are part of the graph, just a faint pencil line to give you a sense of what it looks like. Okay, sketch the graph of y equals negative 1/5 sine of half x. So the negative out the front means that our shape is a reflected sine graph, so it's going to go down first and then up. It's one complete period. Our amplitude is 1/5. Our period, so having a half in here means dilation by a factor of 2 from the y-axis. So the period is actually going to get doubled. If we use our formula, 2 pi on n, in this case 2 pi on 1/2, that's 2 pi times 2, sorry. Dividing by half is the same as timesing by 2, and so that is 4 pi. We're drawing this graph over a different domain, negative 2 pi to 2 pi. That has a span of 4 pi, so we're only going to see one period here. Okay, but it is going to go from negative 2 pi to 2 pi. Okay, so again, thinking about drawing your axes, so we're going to need our y-axis in the middle, given the domain we've got. Our x-axis is also in the middle, because we haven't translated up or down at all. I'm going to draw in some guidelines for my maximum value, which in this case will be 1/5, and my minimum value, same distance below, which will be negative 1/5. Okay, we want to go from negative 2 pi to 2 pi. So if I use that span there for 2 pi, I'm going to use the same kind of distance over here for negative 2 pi. It's about symmetric. I'm going to halve that. That's going to be pi, negative pi. Okay. And in fact, because the period is 4 pi, in marking those points, we have in fact divided the period into 4, and that's all we're going to need in order to get the graph right. Okay, so this time, again, let's start at 0 because we sort of haven't started at the end of a period. If we haven't gone to the left or right, so starting from 0, our graph is going to go down and then back up, okay? Which means that out here, it's going to go this way. So just to give yourself that sense, so it's going to start at 0, halfway along the period will be at 0, at the end of the period, which will be 4 pi, it would also be at 0, but that's outside the domain. So following the pattern backwards, here at negative 2 pi will also be at 0. As I said, the graph, because of the reflection, it goes down first and then up. And so actually we're going to go this way. So we should be at the minimum value there at pi and at the maximum value there at minus pi. Okay, so joining our dots, as I said, they don't all have to be as complicated as the last two. The last two, were complicated by the fact that we had sort of 3 and 4 periods, so quite a lot of repetition. Now, when you draw your sine curves, you want to make sure, you'll notice I erased one of my earlier ones, and that was because I drew it looking quite like a semicircle. It's really important that it doesn't look like a semicircle. Each lump, I guess, is probably, it's not a parabola by any means, but it's more like a parabola shape than it is like a semicircle. Okay, points. So if this is 2 pi, this is pi, so that is the point pi negative 1/5, and this will therefore be negative pi positive 1/5. Y-intercept and x-intercept at 0, 0, and we've got 2 pi and negative 2 pi marked. Without too many points, you might choose to mark them as coordinates. And 0, 0 if you want, but not necessary. Okay, and then our final example here, sketch the graph of negative 10 cos of pi on 4x. Okay, a couple of things to look at here. So shape a negative cos graph, so it's going to start at the bottom and go up and finish at the bottom. Okay, our amplitude is 10. Our period in this instance, so here our n value is pi on 4. So period we know is 2 pi on n, which is 2 pi divided by pi on 4, which is 2 pi times 4 on pi. And so what you're going to see here is that the pi's actually cancel out, and this graph has a period of 8. We'll see this quite commonly in application problems, where our period might, for example, be 12 or 24, often we're to do with hours and time. And in that case, the n value will involve pi, so that when you divide 2 pi by something involving pi, the pi's cancel out and you get a x-axis scale that is in terms of whole integers, or at least fractions rather than numbers involving pi. We want to draw this from 0 to 16, so the domain now makes sense when we see what's happening with the period, and so therefore we want to draw 2 complete periods. So 0 to 16. 2 complete periods of this upside down cos graph. So that's going to be 16. We divide that in half, that's 8, so that'll be 1 period. And remember, we want to divide our period into 4 equal sections to get all the points right. Okay, so therefore we're going to need a scale of 2 in this instance. Okay, let's plot out our points. So let's put some guidelines in. So amplitude is 10. Again, doesn't really matter where we draw it as long as we have same distance above and below our x-axis. As a rough idea, so that point there is therefore 10 and this is negative 10. Okay, go back to your shape now. Your graph is an upside down sine curve. Cos curve. So it starts at the bottom. At the end of the period, which is 8, it is also at the bottom. Halfway along the period, it's at the maximum value, which is positive 10. Halfway between your minimum and maximum values is where you cross the x-axis, which will be at 2 and then again at 6. We can then join our dots, again remembering that you've got a turning point at the start there, so make sure you get that curve right. Okay. And so then it's just about repeating. So every time we move 2 along the x-axis, we'll get to the next key point of the function. So back to the x-axis, up to the maximum value, back to the x-axis, back to the minimum value. Now let's continue to join our dots. Let's mark in all our key points. We've got good space here, so I'll do that. 16, negative 10. This is 8, negative 10. This is at 4, positive 10. And then that's a whole period on from there. So period being 8, 12, positive 10. So that's the other thing you can do, plus a period. Okay, so plus 12, plus 8 in this instance takes us to 12. I might mark my y-intercept with its coordinates, 0, negative 10. And then we can mark our x-intercept. So this is 2, 4, 6, 8, 10, 12, 14. Again, you can mark them with coordinates if you've got space, and need to mark them with coordinates if the question specifies that. Okay, work today here just playing around with reflections, amplitude changes and period changes for sine and cos graphs. Again, it's about planning, and it's worth investing that time at the outset. I can't emphasize that more strongly. It becomes particularly important as we start to translate the graph over the next couple of videos.